Hello and welcome back. In this video, I want to talk about the relationship between pressure and depth. And this is something that everybody has experienced before. So this is where, if you swim down to the bottom of a pool, the pressure that the water exerts on your body is greater than the pressure that is exerted when you're near the top of the water. And so what I want to do is I want to come up with a formula that describes this relationship between pressure and depth. And the way we do this is by applying Newton's second law to a bit of water. So over here, I have a small piece of water. And you should imagine this is like a small piece of water that is in like a pool. Okay, so in a pool, the water isn't, there's no net flow of water inside a pool. So the water's not either moving upwards or downwards. And so what this means is, according to Newton's second law, it tells us that the net force in this vertical direction has to be equal to 0. So looking at this bit of water, there are three forces that are being exerted on it. There's the force caused by the pressure on the top of the water, there's the force caused by the pressure on the bottom of the water, and then there is the weight of the water itself. So if we set the forces that are pushing up on the water equal to the forces that are pushing down, we'll have that the force that's pushing up is equal to the pressure at the bottom of the water times the area, and this has to equal to the forces that are pushing down. So that's the pressure at the top times the area plus the force due to gravity. And what I would like to do is I would like to come up with a relationship that tells me the difference between these two pressures. So I'm going to rearrange this as P2 times A minus P1 times A is equal to the weight of the water. And again, as I mentioned in the earlier video, when we talk about liquids, we usually don't want to look at mass because this is something that depends on the amount of liquid we have. It's not a real property of the liquid itself. So I want to rewrite this in terms of the density. So remember, we have that mass density is equal to mass divided by volume. So this means that mass is equal to mass density times volume. So I could rewrite this as the mass density of the liquid times its volume times G. And now the last thing I want to do is let me rewrite this a little bit. So I could write this as rho G times volume. I'm running out of room here, but the volume of this, if we think about this, so we have this area up here and the water has a height h. So the volume of this is equal to the area times the height. So this is the volume. So now I want to rewrite this left side a little bit. So let me go ahead and rewrite this. This is P2 minus P1 times A. Here I've just factored out this area because it's the same for both of them. And that's going to be equal to rho G times the area times the height. Right? So it's rho G times the volume. And now what I want to do is, because I'm looking for the formula for the difference in the pressures, I want to divide both sides by area. And if I do that, I'll see that the difference in these two pressures is equal to rho GH. So this is the formula that tells you the difference between the pressure at the top of something and the pressure at the bottom of something. It's just equal to this rho GH. And the one thing you want to keep in mind whenever we're doing these types of formulas is just remember that the pressure at the bottom is going to be greater than the pressure at the top. Okay, so it's the pressure at the bottom minus the pressure at the top is equal to rho GH, where h is the difference in the heights of these 2 points. And so it turns out that we can actually use this relationship between pressure and depth to create a device that measures atmospheric pressure. So I have an example of such a device over here. And the basic idea behind this is that you would have a pool of liquid. It'd be open to the atmosphere, and then you would place one end of a tube into this pool, and then you would hook up the other end of this tube to a pump, and you would pump out all of the air that's inside this tube. And when you do this, what will happen is that some of the mercury inside this pool will get drawn up into this pipe. And this is basically the same type of idea as like drinking from a straw. So when you drink from a straw, what you do is you reduce the pressure at the top end of the straw, and when you do this, you'll pull some of the liquid up into the straw. Now, however, it turns out that if this tube is long enough, then even when we make the pressure at the one end of this tube 0, the liquid will only go up to a certain height. And by measuring how far the mercury gets drawn up into this tube, we can figure out what the pressure is outside. So the basic idea behind this is that we know that the difference in pressure between the top and bottom of something is equal to rho GH. And as I said before, historically what they would use is they would use mercury for their liquid. And mercury has a density of 13,500 kilograms per cubic meter. So remember, delta P is the pressure at the bottom minus the pressure at the top. So we have the pressure at the bottom minus the pressure at the top. But in this case, the pressure at the top is 0 because we're going to completely pump out the top of this pipe. And so if we want to figure out how far the mercury will be drawn up this tube, we can just solve for H. So if we do that, we see that the height that the mercury will be drawn up this pipe is going to be equal to the pressure at the bottom, which remember is just equal to atmospheric pressure because this plate is going to be open to the atmosphere. So we have atmospheric pressure divided by the density of mercury, which is this 13,500 kilograms per cubic meter, times G. And if you plug all this into a calculator, what you'll see is that the mercury will be drawn 760 millimeters up this pipe. And this unit of measurement, a millimeter of mercury, is called a torr. So we would say that atmospheric pressure, so 1 atmosphere, is equal to 760 torrs. So let's go ahead and look at an example. This first example says, the heart applies a pressure of 1.9 times 10 to the 5th pascals on the blood in your body. The brain is located approximately 0.45 meters above the heart. The question asks us to determine blood pressure at the brain if the density of blood is 1,060 kilograms per cubic meter. So we know that the difference in pressure is equal to rho GH. And remember, this difference is the pressure at the bottom minus the pressure at the top. So if we think about a person, their heart is somewhere in their chest and their brain is up here at the top of their head. So this difference in pressure is the pressure of the blood at their heart minus the pressure of blood in their brain. And this is going to be equal to the density of blood times gravity times the difference in the height of these two places. So if I'm solving for the pressure in the brain, this is going to be equal to the pressure in the heart minus rho GH. And again, this should make sense, right? The pressure in the brain is going to be less than the pressure at the heart because the brain is further up than the heart. So we're going to be subtracting this difference, rho GH. So now if I just plug these numbers into a calculator, what I'll see is that the blood pressure in the brain is equal to 1.85 times 10 to the 5th pascals. So the blood pressure really doesn't change a whole lot between the heart and the brain. So let's go ahead and look at one more example. This example says we have two identical containers that are connected together by a very thin pipe which has a valve that can be either opened or closed. Initially the valve is closed so that no fluid can flow from one container into the other. Container 1 holds mercury and container 2 holds water. Both containers are filled to 1 meter above the bottom of the container. When the valve is opened, because mercury is more dense than water, some of the mercury moves from its container into the container that's holding the water, causing the height of the water to rise. The question asks us to determine the final height of the water in container 2. And we're told that the density of mercury is equal to 13,600 kilograms per cubic meter, and the density of water is 10 to the 3rd kilograms per cubic meter. So here's a picture just illustrating what we have. So on the left side we have a container that holds water, and it's initially 1 meter deep. On the right side we have a container that's holding mercury that's also 1 meter deep. And these two containers are connected together by a thin pipe which has a valve. So at some time this valve is going to be opened, and because the mercury is more dense, some of the mercury in this container will flow into the container that's holding the water, and this will cause the water level to rise. And what we're asked to do is find this height right here. So this is the total height of all of the liquids in this container over here. So this is container 2, just for reference, and this is container 1. So this is going to take a little bit of space, so let me go ahead and open up OneNote. So I've gone ahead and I've drawn another picture of this problem, and the basic idea behind this problem is that the pressure at the bottom of container 1 is going to be greater than the pressure at the bottom of container 2, because mercury is more dense than water. So because the pressure at the bottom of this container is greater than the pressure at the bottom of the container holding water, some of the mercury will flow into the container that's holding water. Okay, because there's a greater pressure over here on the right than there is on the left. And this mercury is going to flow from container 1 into container 2 until the pressure at the bottom of these two containers is equal to each other. So this is the basic equation that we're going to use to solve this problem, is that we need the pressure at the bottom of container 2 to equal the pressure at the bottom of container 1. And we can use the pressure and depth relationship to relate these two things and solve for the final height of the fluids in container 2. Now, in order to do this, I need to introduce some notation. So let me go ahead and I'm going to call the final height of all the fluids in container 2. This is what we're trying to solve for. I'm going to call this H subscript 2. And I'm not going to worry about putting a final here because the initial heights, let me go ahead and write this up here. Remember, both of these initial heights is just 1 meter. So anytime I refer to the initial heights, I'll just explicitly write 1 meter. And this will help keep our notation a little bit simpler. Now, I also need to worry about the amount of mercury that's going to flow from container 1 into container 2. So I'm going to call the depth of the mercury that's in this container, I'll call this H subscript Hg2. Okay, so this is the height of the mercury in container 2. And I use Hg because Hg is the elemental symbol for mercury. And over here on the right, I could call this the height of the mercury that's in container 1, but this is also just equal to the height of all the fluids that's in container 1. So either one of those mean the same thing. So the basic idea here is that we have that the pressure that's in container 2 needs to be equal to the pressure that's in container 1. So the pressure at the bottom of container 2 is equal to the pressure that's caused by 1 meter of water. Remember, no water leaves this container, so this is still just 1 meter of water, plus the pressure caused by this extra mercury. So the pressure at the bottom of container 2 is the pressure caused by H2O plus the pressure that's caused by the mercury that's in container 2. And this has to be equal to the pressure that's caused by the mercury in container 1. So the pressure caused by water, remember the pressure-depth relationship is that the change in pressure is equal to rho GH. So here both of these containers are open to atmosphere, so we can kind of ignore that. The pressure at this point is going to be equal to rho GH plus that atmosphere. So right here, we've got this extra rho GH caused by the water. So this is going to be equal to, so the pressure that's caused by the water is equal to the density of water times gravity times the height of the water, which in this case is still just 1 meter, plus the density of mercury times gravity times the height of the mercury that's in this container. So remember, I'm denoting this as H subscript Hg2 because this is the amount of mercury that's in this container 2. And this has to equal the pressure at the bottom of container 1. And remember, we only have mercury in container 1, so this is just going to be equal to the density of mercury times G times the height of the mercury that's in this container. So at this point, what we need to do is we need to find some way to relate these different heights, because we've got the height of the mercury that's in container 2, and we've got the height of the mercury that's in container 1, and we want to come up with some way that we can relate all these so that we can reduce the number of unknown values that we have, because right now we've got too many unknowns to solve this. So let's go back up here to the top. If we think about this, initially we have some volume of mercury that's in this container, and afterwards some of the mercury is going to move from this container into container 2, but the total volume of the mercury doesn't change, right? So we're not losing any mercury. Any of the mercury that leaves container 1 goes into container 2. So what we can say is, because these two containers are identical, we can say the height of the mercury that's in container 1 plus the height of the mercury that's in container 2 have to be equal to the initial depth of the mercury, which was 1 meter. So we have that the heights, let me go ahead, maybe I'll write this over here on the right. We have the height of the mercury that's in container 2 plus the height of the fluids that are in container 1, remember we only have mercury in container 1, is equal to 1 meter. So what I can do is I can plug this equation into here, and I can rewrite this just in terms of the height of the mercury that's in container 2. So let me go ahead and do that. So I could say that H1 is equal to 1 meter minus the height of the mercury that's in container 2. So if I plug this into here, what I'll see is it will have the density of water times G times 1 meter plus the density of mercury times G times the height of the mercury that's in container 2 has to be equal to the density of mercury times G times the height of the mercury that's in container 1, but this is 1 meter minus the height of the mercury that's in container 2. So now at this point I have an equation, and the only unknown in this equation is the height of the mercury that's in container 2. So that's what I want to solve for. So I want to take everything that has the height of the mercury in container 2, I want to take all of those things and move them to one side of the equal sign, and I want to take everything else and move it to the other side of the equal sign. So to do this, I'm going to subtract this so that I move this over to the right side. So that's going to remove this from the left side of the equation, and then I need to get this term over to the right side. So to do that, I need to add to both sides the density of mercury times G times the height of the mercury that's in container 2. So if I do that, what I'll see is that on the left side I have 2 times the density of mercury times G times the height of the mercury that's in container 2 is equal to, and over here, so this one cancels with this, and on the right side I have the density of mercury times G times 1 meter minus the the pressure caused by water. So this is equal to the density of water times G times 1 meter. So finally, if I solve for the height of the mercury, so I'm going to divide both sides by this 2 rho of mercury, the density of mercury, times G. So the G's will cancel everywhere. We have 1 meter out here, so I can actually factor this out. So what I'm going to see is I'm going to see that the height of the mercury, it's in container 2, is equal to 1 meter times the density of mercury minus the density of water divided by 2 times the density of mercury. So this is the final height of the mercury that's in container 2. Now that wasn't really exactly what I asked you to solve for. So I asked for the total height of all of the fluids that are in container 2. But if we think about this, none of the water that was in container 2 ever leaves container 2. We're only going to add mercury into this, and that's going to push the water up. So we still have 1 meter of water in container 2. So the total height of the fluids that are in container 2 is just equal to the height of the mercury that's in container 2 plus 1 meter for the water. So the final height in container 2 is just equal to 1 meter plus this. So we have 1 meter plus 1 meter times the density of mercury minus the density of water divided by 2 times the density of mercury. And if I plug all these numbers into a calculator, see I have a cheat sheet here, the final height in container 2 is going to be equal to 1.463 meters. And so that's how we solve this problem. And at this point, I think I'd like to end this video, and in the next video, I'm going to talk about Archimedes' principle, which is the principle behind buoyancy. So it turns out that because pressure is greater at greater depths, that this difference in pressure can actually exert an upward force on objects when they're submersed in a liquid.